Welcome to This Explainer. When you hear the word epidemiology, it's super easy to just picture dry statistics, endless boring spreadsheets, or dusty old medical journals. But honestly, the truth is entirely different. Epidemiology is literally the ultimate disease detective's toolkit. It's the science of figuring out the hidden patterns, the precise causes, and the real-world effects of health conditions across whole populations. So today, we're not just going to look at numbers. We are exploring the critical, everyday mathematical tools that public health experts actually use to predict risk, trace the source of outbreaks, and ultimately save lives.
Okay, let's dive right into this. Here is our agenda for today. First, we'll look at incidence and measuring new risk. Second, prevalence and understanding total burden. Third, we'll connect the two. Fourth, we're covering attack rates and outbreaks. And finally, we'll wrap up with real-world tracking using the SARS timeline.
Section 1. Incidence. Measuring new risk. Let's kick things off with our very first major concept. To truly understand a disease and how it behaves in a community, we first have to measure the speed at which it's attacking new people. And I really want to emphasize that word, new. Incidence is strictly the measure of new clinical cases developing in an initially disease-free population at risk over a specified window of time. Why is this absolutely crucial? Well, because incidence is the only baseline measure that directly quantifies absolute clinical risk. It isolates that exact transition from being perfectly healthy to becoming sick. So if you want to know your personal risk of catching a bug this winter, incidence is the exact number you're looking for. So, how do disease detectives actually calculate this? The formula is beautifully straightforward. You take the number of new cases of a disease during a specific period. That's your numerator. Then you simply divide that by the total population at risk during that exact same period. That's your denominator. Finally, you multiply by a base factor, typically 100,000, so you end up with a standardized rate that's super easy to understand and compare across different cities or even countries.
And this brilliantly illustrates how it works in practice. Let's look at a hypothetical city. We'll call it Atlantis. Over a 6-month period, Atlantis records 26 new active cases of tuberculosis. The population of Atlantis is 183,000. Following our formula, we just divide those 26 new cases by the 183,000 people at risk. Multiply that by 100,000, and boom, we get an incidence rate of roughly 14.2 new TB cases per 100,000 people. This gives us a crystal clear standardized measure of the immediate risk in that specific city.
Now, let's take this to a massive real-world scale. During a huge outbreak of the chikungunya virus, which is a really nasty mosquito-borne illness, epidemiologists calculated a 1-year cumulative incidence of 24.2 per 1,000 persons. By translating raw, chaotic counts of hundreds of thousands of sick people into this one simple rate, experts could paint a clear picture of the massive population risk. They understood exactly how fast the virus was spreading through the community.
Section 2. Prevalence. Understanding total burden.
So the main takeaway so far is that incidence tells us about the immediate threat. But what about the folks who are already sick? That requires a totally different tool. While incidence tracks new threats, prevalence measures the heavy reality of what is already here. Prevalence is the total proportion of a population possessing a specific disease. And by that we mean both newly diagnosed cases and long-standing surviving cases at a designated point in time. Prevalence doesn't care when you got sick, it only cares if you are sick right now. It's like a static snapshot that tells us about the overall societal burden. It tells health ministers how many hospital beds they need, how much medication to stock up on, and what the long-term care requirements are going to be for a community.
To keep these two straight in your head, I absolutely love this visual metaphor. Think of incidence as a leaky faucet. It's the flow of new water dripping down. That's your immediate risk. Prevalence, on the other hand, is the sink right below it. It is the total volume of water that is already collected in the basin. The sink holds all the water that has dripped in and hasn't yet drained away. So incidence is the flow, prevalence is the existing burden. Returning to our Atlantis example really highlights this difference. Remember, the incidence, the new cases dripping from the faucet, was only 14.2 per 100,000. But if we check the city registry on that exact same day, we find there are 264 total active TB cases. These are people who got sick recently, plus people who got sick months or even years ago and are still fighting it. When we divide that 264 by the 183,000 population, we get a point prevalence of 144.2 per 100,000. Because TB is a chronic condition that sticks around, the prevalence burden in the sink is much, much higher than the incidence dripping from the faucet. Section 3. Connecting incidence and prevalence. Now, these two numbers don't just exist in isolation. They are mathematically linked in a way that reveals incredible insights about how diseases actually behave over time. Under stable conditions, the elegant formula connecting them is this: prevalence equals incidence multiplied by the average duration of the disease, P equals I times D. The total pool of sick people is simply the rate of new people getting sick multiplied by how long they stay sick before they either recover or pass away. It is a brilliant, brilliant way to model the natural history of any condition. And this simple equation creates what epidemiologists call the success paradox. Okay, imagine a scientist invents a revolutionary new treatment for an incurable chronic disease. It doesn't cure the patients, but it stops them from dying. What happens to the math? Well, the average duration of the disease skyrockets. And because prevalence equals incidence times duration, the prevalence suddenly spikes upwards. If a health minister only looked at the total number of cases, they might totally panic. But a rising prevalence isn't always bad news. In this case, it actually means our healthcare system is successfully keeping people alive with chronic conditions. It's a massive medical triumph disguised as a scary statistic. Section 4. Attack rates and outbreaks.
Now let's pivot away from chronic conditions for a second and look at acute, fast-moving scenarios. When a sudden outbreak hits, like say a contaminated food source at a banquet, disease detectives use specialized metrics to hunt down the exact source of danger. In these intense, localized situations, we use the attack rate. It's a specific variant of incidence that tracks the proportion of people who develop an acute illness right after a highly compressed exposure. It doesn't measure a rate over a whole year, it measures the immediate fallout of a single specific event. It is literally the ultimate investigative tool for pinpointing the exact vehicle of infection. Let's look at how this plays out in a real-world investigation of a sore throat outbreak at a big dinner. Epidemiologists use a cross-tabulation table to act as detectives, separating out all the variables. They go in and ask everyone exactly what they ate. Look at the top row. Of the 75 people who ate both the egg salad and the tuna, 60 got sick and 15 stayed well. By breaking down every single combination of food, they can mathematically isolate which specific item is the culprit, easily controlling for all the other confusing variables. When we calculate the attack rate for that specific group, the 66 folks, divided by the 75 total exposed, we reveal a massive 80% attack rate for those who ate the egg salad and tuna combo. By comparing this 80% to the attack rates of people who only ate tuna or only ate egg salad, investigators can isolate the true infective vehicle. And it turns out, in this specific case from the source data, the egg salad was the solo culprit driving the entire outbreak. Now, a quick side note here, because it's super important to briefly contrast attack rate with another metric you hear in the news all the time, the case fatality rate, or CFR. They measure two very, very different dangers. Attack rate measures how easily a disease spreads, its infectivity. CFR, on the other hand, measures how deadly it is once you've already caught it, its lethality. A disease might have a high attack rate, but a very low CFR, meaning it spreads absolutely everywhere, but rarely causes severe harm. Knowing the difference between the two is key to assessing true risk. Section 5. Real-world tracking. The SARS timeline. Let's pull this all together and apply these concepts to a terrifying, real-world historical event. Let's see descriptive epidemiology in action, tracking the first 2 months of the original SARS outbreak in 2002. When an unknown disease emerges, epidemiologists immediately build a descriptive framework based on 3 foundational pillars: person, place, and time. They map out who is getting sick, looking at occupations or demographics. They map out where it's happening, identifying geographic clusters or specific hospitals. And they map out when, creating epidemic curves to track the timeline. This organizes raw, chaotic surveillance data into actionable health defense strategies. And looking at the timeline of SARS, we see this pattern play out perfectly. In November 2002, the math started ticking with a zoonotic spillover in Flushan, China. Basically, the virus jumped from the wildlife trade to a human index case. By mid-December, surveillance maps showed independent transmission chains popping up in neighboring cities like Haiyuan and Shenzhen. Then, by late December, the most critical shift happened. Critically ill patients were transferred to major hospitals in Guangzhou. Without proper protective equipment, these intensive care units became massive amplification engines, infecting huge numbers of healthcare workers. The descriptive data proved the outbreak had exploded from a single market into a multi-centric urban crisis across the Pearl River Delta. Which brings us to a really vital question. How does mapping all this math, incidence, prevalence, attack rates, spatial clusters, how does it actually stop the next pandemic? How does it bridge the gap between tracking history and defending our future? Well, here is the incredible takeaway. These aren't just abstract numbers. They are the actual blueprints for saving lives. A localized spike in incidence tells us exactly where to invest in immediate primary prevention, like rolling out vaccines or closing a contaminated water source. Tracking prevalence tells governments exactly where to build long-term safety nets and fund chronic care. Attack rates give us the precision to trace and eliminate immediate exposures. Epidemiology literally takes the raw chaos of biology and translates it into targeted, real-world public health action.
I want to leave you with this provocative thought. If incidence measures the spark and prevalence measures the raging fire, what hidden data is starting to smoke right now in our global community? Disease detectives are out there right now calculating the unseen mathematical currents of global health that protect us all. Keep that in mind the next time you see a health headline. Thanks so much for exploring this with me.